The next topic we want to cover is the solenoid, sometimes referred to as a coil or electromagnet. It's basically a wire wrapped around a core. We're going to deal with air. Now, please keep in mind that if we put inside of here, because the thing really is almost like a toilet paper tube, it's just a tube going around like that. If we insert a ferromagnetic material, it will make the magnetic field much stronger. So, inserting a ferromagnetic material into the coil makes the field, that's the magnetic field, stronger. But we're going to deal with air. And we're not going to worry about sticking in there something else other than air inside the coil. Now, picture the current coming here. It actually goes behind the coil, up around in front, behind the coil, up around in front, behind the coil, up around in front and down. If we were to take a look at this and say, okay, there's this wire right there, is if I took this coil and sliced it lengthways right across, at that point the current would be coming out of the page. So I'm going to put a dot here, and dot here, because in all those cases the current is coming out of the page. Down below, the current's going into the page at these points. Now, next thing we want to do is we want to figure out what the magnetic field direction is for each one of these wires. Well, pretty simple. Thumb's coming out of the page for the ones above. Fingers wrap around like this. So it's going to be going counterclockwise for all these guys. So that's going to be counterclockwise. Draw it like this, just the way I'm drawing it. Counterclockwise, counterclockwise. The ones down below, thumb goes in, fingers wrap around like this. So that's going to be clockwise. Just like that. Now, if we take a look inside of the coil, all the magnetic fields on the top are pointing towards the right inside the coil. On the bottom, they're all pointing towards the right. So in this direction, we wind up with a strong, uniform magnetic field inside of the coil. It's a strong, uniform magnetic field. And that's your B right there. Now this looks just like a bar magnet. It'll come out, go around, enter this side. This guy will do the same exact thing. Go like this. And we get the same stuff going on here. It comes up, goes around like that. Make sure we do not cross the field lines because they do not cross. And there's our magnetic field. To solve this, guys, first of all, we can use a right-hand rule to determine the direction of the magnetic field. In this case, my fingers wrap around in the direction of the current flow. So current's going up and around like that. My fingers wrap in the direction of the current flow. And my thumb points in the direction of the magnetic field. Current's coming out. Put some arrows here so you can see. Arrows going down, arrows. There we go. So fingers come up, over and around like that. My magnetic field's going in that direction, which means I'm going to wind up with a north pole over here and a south pole towards the right. Okay, right-hand rule. My thumb is going to represent the direction of the magnetic field. And my fingers, because we curl around, is going to represent the direction of the current. Now, B equals mu 0 Ni. To find out how strong, and this is for a long, thin coil, my magnetic field strength at the poles, that's at the ends here, and internally on the solenoid is equal to mu0, permeability of free space, times n. N is the kicker. N is the number of turns per unit length. N is number of turns per meter. If you want to think about it as the wrap density on it, how dense this thing is wrapped per unit length, you'll be okay with that. And I, of course, is the current going through there. Now, what happens to the field strength? Well, we already talked about it. If we put a highly magnetically permeable object into there, it increases the strength of the coil. And no longer that's going to hold true. All right, that's it.